So let's talk about something that has kept physicists awake at night for the last 100 years. Something so fundamentally strange, so deeply counterintuitive that Albert Einstein, one of the greatest minds in human history, spent the last 30 years of his life refusing to accept it was true. I'm talking about quantum mechanics. And before you check out, because that sounds like a textbook your physics teacher assigned on a Friday afternoon, stay with me. Because quantum mechanics is not just some dry academic subject reserved for people with PhDs and too much coffee. It is the operating system of the universe. It is the reason your phone works. It is the reason the sun shines. It is the reason anything solid exists at all. It is, without any exaggeration, the most successful scientific theory ever developed by human beings in the entire history of science. It also makes absolutely no intuitive sense whatsoever, and I mean that literally, not metaphorically. Richard Feynman, who won the Nobel Prize in Physics and was basically the rock star of the quantum world, famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This wasn't false modesty. This was a genuine warning from one of the people who understood it better than almost anyone alive. So, here's what we're going to do today. We're going to build up quantum mechanics from scratch. Starting from the very beginning. No assumed knowledge. No prerequisites. We're going to cover wave-particle duality, superposition, the observer effect, entanglement, the uncertainty principle, quantum tunneling, wave function collapse, the measurement problem, the many worlds interpretation, and quantum computing. And we're going to end somewhere that is genuinely going to make you question the nature of reality itself. Let's start at the beginning. Part 1. The classical world and why it seemed perfect. For most of human history, physics worked. Beautifully, elegantly, precisely. Isaac Newton in the late 1600s described the laws of motion and gravity with such accuracy that we use them to land spacecraft on the moon 300 years later. James Clerk Maxwell, in the 1800s, unified electricity and magnetism into a single elegant theory. Thermodynamics explained heat and energy. The kinetic theory explained gases. By the end of the 19th century, some physicists genuinely believed that physics was essentially finished, that the major work was done, that the universe was a giant clockwork machine running according to deterministic laws that we had essentially figured out. Lord Kelvin, one of the most eminent physicists of the era, reportedly said in 1900 that there was nothing new to be discovered in physics. All that remained was more and more precise measurement. He could not have been more wrong. Because at the same time he was saying this, two small clouds were gathering on the horizon of physics. Two experimental results that classical physics simply could not explain. And those two clouds would eventually blow up the entire edifice of classical physics and replace it with something utterly alien. The first cloud was the ultraviolet catastrophe. When physicists calculated the radiation emitted by a hot object using classical physics, they got an insane result. Classical theory predicted that a hot object should emit infinite energy at high frequencies. Infinite, which is obviously not what happens when you look at a glowing light bulb. This became known as the ultraviolet catastrophe, and it was a serious problem. The second cloud was the photoelectric effect. When you shine light on certain metals, electrons get knocked off the surface. Classical physics predicted that brighter light should knock off electrons with more energy. But experiments showed that the energy of the ejected electrons depended on the frequency of the light, not the brightness. Dim, high-frequency light knocked off high-energy electrons. Bright, low-frequency light knocked off nothing at all, no matter how bright you made it. Neither of these results made any sense in classical physics. And the solutions to these two problems launched the quantum revolution. Part 2. Planck, Einstein, and the birth of the quantum. The ultraviolet catastrophe was solved in 1900 by a German physicist named Max Planck, and he solved it by making what he himself described as an act of desperation. Classical physics assumed that energy could be exchanged in any amount, smooth and continuous, like water flowing from a tap. Planck showed that if you instead assume energy can only be exchanged in discrete chunks, in packets of a minimum size, the math worked out perfectly. The calculated radiation matched the experimental results exactly. He called these packets quanta, from the Latin word for amount. But here's what's interesting. Planck himself didn't really believe quanta were physically real. He thought they were a mathematical trick, a useful fiction that happened to give the right answer. He fully expected that one day someone would find a more satisfying classical explanation. That day never came. 5 years later, in 1905, a 26-year-old patent clerk named Albert Einstein took Planck's idea seriously. He applied it to the photoelectric effect. He said, "What if light itself actually comes in discrete packets? What if light is not a continuous wave, but is made of individual particles, each carrying a specific amount of energy determined by its frequency? These light particles would later be called photons." And Einstein's explanation of the photoelectric effect was perfect. High-frequency photons carry more energy, so they knock off high-energy electrons. Low-frequency photons don't carry enough energy to kick off any electrons regardless of how many of them you fire. The intensity of light is just how many photons there are, not how much energy each one carries. It worked. It explained everything, and it won Einstein the Nobel Prize. Not relativity, by the way. Photoelectric effect. Quantum mechanics. But now there was a problem. A deep, serious problem that nobody could immediately solve. Because Maxwell's equations, which were incredibly well confirmed, described light as a wave. And now Einstein was saying light was a particle. Which was it? A wave or a particle? The answer, as it turned out, is both. And neither. And this is where things start to get genuinely strange. Part 3. Wave-particle duality. The first sign of strangeness. Wave-particle duality is the principle that quantum objects like photons and electrons exhibit properties of both waves and particles depending on how you look at them. And this isn't a limitation of our understanding or our instruments. It's a fundamental feature of nature. Let's think about what a wave is. A wave is a disturbance that spreads through space. Ocean waves, sound waves, radio waves. Waves can interfere with each other. When two waves overlap, where two peaks meet, you get a bigger peak. Where a peak and a trough meet, they cancel out. Waves have wavelength, frequency, amplitude. They spread out and diffract around obstacles. These are wave properties. And let's think about what a particle is. A particle is a localized object with a definite position and momentum. A baseball, a grain of sand. When you detect a particle at a specific location, it's there. Not spread out, not in multiple places. There. Particles have mass. They travel in straight lines unless acted on by forces. They bounce off things. These are particle properties. These two descriptions seem mutually exclusive. Something is either a wave or a particle. It can't be both. That doesn't make conceptual sense. And yet that's exactly what quantum objects are. When you run an experiment designed to detect wave behavior, light behaves like a wave. When you run an experiment designed to detect particle behavior, light behaves like a particle. The experimental setup determines which aspect of reality you see. And this isn't just light. Electrons do it. Atoms do it. Even molecules made of dozens of atoms have been shown to exhibit wave-like interference behavior. The quantum world is fundamentally neither waves nor particles. It's something else entirely that we don't have a good classical word for. Something that, in certain experiments, shows wave properties and in certain experiments shows particle properties, but is fundamentally neither. The best demonstration of this is the double slit experiment. And this is where I need you to pay close attention because this experiment is, in the opinion of many physicists, including Feynman, the central mystery of quantum mechanics. The experiment that most clearly shows how different the quantum world is from anything our intuition is prepared for. Part 4. The double slit experiment, the most important experiment ever done. Imagine you have a barrier with 2 narrow slits in it, and on the other side of the barrier is a screen that records where things hit it. Now imagine you're firing tennis balls at this barrier. Some go through the left slit, some go through the right slit. On the screen, you get 2 clusters of marks, one behind each slit. Exactly what you'd expect. Classical. Intuitive. Boring. Now do the same experiment with waves. Make waves on water and send them at the barrier. The waves go through both slits simultaneously. On the other side, the waves from each slit spread out and interfere with each other. Where crests meet crests, you get amplified waves. Where crests meet troughs, you get cancellation. On the screen, you get an interference pattern. Multiple bands of high and low intensity spread across the screen. This is what waves do. Now do the experiment with light. You get the interference pattern, multiple bands. Light is a wave. Great. Thomas Young did this in 1801 and confirmed it. But then things get complicated because now we use a very dim light source, one that fires individual photons one at a time. Single particles of light, 1 per second, each going through the apparatus alone, with no other photon around to interfere with. At first, each photon just hits a single spot on the screen, one at a time, like little particles. Nothing weird. But over time, as thousands of individual photons accumulate, something remarkable happens. The pattern that builds up on the screen is the interference pattern. Bands of high density where many photons landed, separated by bands of low density where almost no photons landed. The same pattern you'd get if light were a wave going through both slits and interfering with itself. But these were individual particles. There's nothing to interfere with. Each photon went through the apparatus alone. And yet somehow the overall pattern that emerged is an interference pattern, as if each individual photon somehow knew about both slits, as if each individual photon went through both slits simultaneously and interfered with itself. Physicists thought, okay, maybe the photons really are going through both slits and we just can't see it. Let's put detectors at the slits to watch and find out which one each photon actually goes through. So they ran the experiment again with detectors at the slits to observe which slit each photon passed through. The interference pattern disappeared. With detectors running, the photons started behaving like particles again. Each went through one slit or the other. 2 clusters on the screen. No interference. They removed the detectors. The interference pattern came back. They put the detectors back. The interference pattern disappeared again. Over and over, every time. With detectors watching, particles. Without detectors watching, waves. The photon's behavior depended on whether it was being observed. And before anyone suggests there must be a mechanical explanation, that the detectors are physically disturbing the photons, and that's why the pattern changes, physicists have been extremely careful about this. They've run versions of the experiment where the detector at the slit records which path, but the record is immediately destroyed before anyone looks at it. The interference pattern comes back. The physical disturbance from the detector was the same, but the information about which path was not retained anywhere, and the interference pattern returned. It's not the physical interaction that matters. It's whether the which path information exists somewhere in the universe. If it does, no interference. If it doesn't, interference. The universe somehow responds to the availability of information. This result has been confirmed thousands of times in dozens of variations with electrons, atoms, molecules. It is one of the most reproducible and well-confirmed results in all of science, and it has no classical explanation. None. Not even close. Part 5. Superposition. Being two things at once. To explain what's happening in the double-slit experiment, we need the concept of superposition. And superposition is perhaps the most central and the most philosophically strange idea in quantum mechanics. Superposition is the principle that a quantum system can exist in multiple states simultaneously until it is measured. Not that we don't know which state it's in. Not that it's secretly in one state and we just can't tell. It genuinely, physically exists in multiple states at the same time. When the photon is traveling through the apparatus before the detectors, it is in a superposition of going through the left slit and going through the right slit, both paths at once. This superposition is what allows the wave-like interference pattern to appear. Because interference requires a wave going through both slits simultaneously. When a detector is placed at the slits, it interacts with the photon to determine which slit it went through. This interaction forces the superposition to resolve into a definite state. The photon is now in the state of having gone through the left slit or the state of having gone through the right slit. Not both. One. And once it's in a definite state, there's no superposition, no interference, just a particle going through one slit. This resolving of superposition into a definite state is called wave function collapse. And we'll talk about it in detail shortly. But first, the most famous illustration of superposition, Schrödinger's cat. Part 6, Schrödinger's cat, a thought experiment that changed physics, in 1935. Austrian physicist Erwin Schrödinger proposed a thought experiment specifically designed to highlight what he saw as an absurdity in quantum theory. He was trying to show that applying quantum superposition to macroscopic objects leads to ridiculous conclusions. The setup is this. You put a cat in a sealed box. Inside the box, there's a tiny piece of radioactive material, a Geiger counter to detect radiation, a vial of poison, and a mechanism that smashes the vial if the Geiger counter detects a decay event. If a single radioactive atom decays, the poison is released and the cat dies. Now, radioactive decay is a quantum process. An unstable nucleus exists in a superposition of decayed and not decayed until it's measured. Before anyone opens the box and looks, the nucleus is in superposition. Following quantum logic consistently, before you open the box, the nucleus is simultaneously decayed and not decayed. Therefore, the detector is simultaneously triggered and not triggered. Therefore, the poison is simultaneously released and not released. Therefore, the cat is simultaneously dead and alive at the same time, in the same box. Schrödinger found this conclusion absurd. He wasn't genuinely claiming cats could be alive and dead at the same time. He was exposing what he thought was a flaw in quantum theory. The theory works beautifully for electrons and photons, but when you try to scale it up to everyday objects, you get nonsense. But here's the uncomfortable thing. Schrödinger was more right than he intended. Not about actual cats. Nobody believes macroscopic superpositions exist for long in the real world. But the principle behind the thought experiment, that quantum superposition is real, and that the rules of quantum mechanics have to apply consistently, is absolutely correct. The reason cats don't actually sit in superpositions of alive and dead has to do with something called decoherence. In practice, a cat is constantly interacting with its environment. Air molecules, photons, the box walls, its own internal thermal fluctuations. Each of these interactions is essentially a tiny measurement. The quantum superposition of the system gets entangled with the environment, and the interference effects that make superposition visible wash out almost instantly. For a single electron, isolated from its environment, superposition can be maintained and measured. For a cat made of 10 to the power of 27 particles, all interacting constantly with each other and their surroundings. The superposition decoheres in an unimaginably short time. So the classical world emerges from the quantum world through decoherence, not because quantum mechanics stops applying to big things, but because big things does interact with so many other things so rapidly that the quantum weirdness becomes unmeasurably small. The underlying reality is still quantum. The classical world we see is an approximation that emerges at large scales. Part 7. The observer effect. Does reality need a witness? The observer effect in quantum mechanics is the fact that the act of measuring a quantum system necessarily disturbs it. And the double-slit experiment showed us that whether or not information exists about which path a particle takes changes its behavior fundamentally. Also, this raises a question that haunted 20th century physics and has not been fully resolved to this day. What counts as an observation? What counts as a measurement? Does it require a human consciousness? Does it require any physical interaction at all? Is the entire universe constantly observing itself into definiteness? Early quantum pioneer Niels Bohr's Copenhagen interpretation essentially said, don't ask that question. Use the math, make predictions, stop trying to picture what's really happening. The formalism works. That's enough. But many physicists found this deeply unsatisfying. John Wheeler, one of the great physicists of the 20th century, spent decades grappling with the role of the observer. He proposed what he called the participatory anthropic principle, the idea that the universe requires observers to bring it into definiteness, that without observation, reality exists only as potentiality. Wheeler took this seriously enough to propose delayed choice experiments, thought experiments, and later actual experiments, where the decision about what kind of measurement to make, wave behavior or particle behavior, is made after the particle has already passed through the apparatus. In the quantum eraser experiment, a delayed choice version of the double slit, physicists can choose after the fact whether to retain or erase the which path information, and the interference pattern appears or disappears accordingly, even though the choice was made after the photon had already traveled through the apparatus. This seems to imply that the photon's past behavior was affected by a future choice, which sounds like backwards causality, which sounds insane. The mainstream interpretation of these results doesn't require backwards causality. It requires that we be very careful about what we mean by the photon state at various times. But these experiments do confirm that the availability of which path information, regardless of when it's obtained or destroyed, determines whether interference occurs. The physical world responds to information in a way that has no classical analog. Most physicists today believe that consciousness is not specially required for wave function collapse. Any physical interaction that records which path information counts. You don't need a brain, you need information to exist somewhere in the physical world. But even this view, the standard view, is philosophically startling. It means reality does not consist of objects with definite pre-existing properties that we passively observe. It means that the properties of particles come into existence through the act of interaction and measurement. The universe is, in some deep sense, participatory. Part 8. Quantum entanglement. Spooky action at a distance. Now we get to the one that Einstein hated most. Quantum entanglement. When two particles interact in certain ways, their quantum states become correlated in a way that persists regardless of how far apart you separate them. These particles are said to be entangled, and the correlations between them are stronger than any classical explanation can account for. Here's the setup. You create two photons together in a process called spontaneous parametric down conversion. This process produces pairs of photons whose polarizations are correlated but in superposition. Neither photon has a definite polarization, but they're correlated. If you measure one and find it vertically polarized, the other will be found horizontally polarized when measured. You send one photon to a lab in Tokyo, you send the other to a lab in New York. When the Tokyo researcher measures her photon and finds it vertically polarized, the New York photon instantly becomes horizontally polarized. not eventually, not after a signal travels between them. Instantly, regardless of the distance. Einstein recognized this result from the mathematics of quantum mechanics and despised it. He called it spooky action at a distance. He wrote a famous paper in 1935 with Boris Podolsky and Nathan Rosen, known as the EPR paper, arguing that this result proved quantum mechanics was incomplete. His reasoning was elegant. Surely, he argued, the photons must have had definite polarizations all along. Polarizations that were set when they were created, like a pair of gloves separated and shipped to different cities. When you find the left glove in Tokyo, you instantly know New York has the right glove. No spooky action, just pre-existing information you didn't know. This idea that particles have definite hidden properties that we haven't measured yet is called a hidden variable theory, and it sounds completely reasonable. The problem is, it's wrong. Part 9, Bell's theorem, the experiment that settled it. In 1964, Irish physicist John Bell did something remarkable. He derived a mathematical inequality, now called Bell's inequality, that any hidden variable theory must satisfy. He showed that if Einstein was right, if particles have pre-existing definite properties, then the correlations between entangled particles measured at different angles could only be so strong. There was a mathematical limit. And if quantum mechanics was right, if superposition and entanglement are genuinely real, then the correlations would be stronger than that limit. Bell had found a way to test, with a real experiment, whether Einstein or Bohr was right. The experiments were done. The most rigorous versions were carried out in 2015, simultaneously by groups in the Netherlands, the United States, and Austria. They closed all the major technical loopholes that had left earlier experiments open to criticism. They measured the correlations between entangled particles detected at widely separated locations. Bell's inequality was violated by a lot. Exactly as quantum mechanics predicted, Einstein was wrong. Hidden variables don't explain entanglement. The correlations are genuinely non-local. They cannot be explained by any pre-existing local properties of the particles. This means one of two things must be true. Either particles don't have definite properties before measurement, which is the standard quantum mechanical view, or there is some kind of faster-than-light influence connecting entangled particles. And since overwhelming evidence rules out faster-than-light signaling through entanglement, because you can't use it to send information faster than light, the standard view wins by default. The universe is non-local. Sorchets, entangled particles are genuinely connected regardless of distance in a way that has no classical analog. Now, before you get excited about teleportation or faster-than-light communication, there's a frustrating catch. You cannot use entanglement to send information faster than light. When Alice measures her photon in Tokyo, she just sees a random result, vertical or horizontal with 50-50 probability. When Bob measures his in New York, he also just sees a random result. It's only when they compare their results through a classical channel, which is limited to the speed of light, that they can see the correlations. The randomness prevents information transfer. The correlations are only visible in comparison. So no faster than light messaging, no quantum teleportation of information. But entanglement is real, and it is being put to practical use right now in quantum cryptography, where it enables provably secure communication, and in quantum computing, where entanglement between qubits is a key computational resource. And philosophically, entanglement means that the universe at its most fundamental level is not a collection of independent local objects. Separated particles can be more deeply connected to each other than to anything in their immediate vicinity. The universe does not respect distance at the quantum level. Part 10. The Uncertainty Principle: Why the Universe Keeps Secrets. In 1927, Werner Heisenberg derived one of the most profound results in the history of physics. A result so counterintuitive that Even today, it's frequently misunderstood, even by people who should know better. Heisenberg's uncertainty principle states that there is a fundamental limit to how precisely you can know certain pairs of physical properties simultaneously. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving and in what direction. The more precisely you know its momentum, the less precisely you can know its position. Mathematically, the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to h bar over 2, where h bar is the reduced Planck constant, a tiny number but not zero. The most common misunderstanding of this principle is that it's about measurement disturbance, that when we try to measure a particle's position, we have to bounce something off it, and that disturbs its momentum. And while that's a real effect, it's not what the uncertainty principle is actually saying. The uncertainty principle is not about the disturbance caused by measurement. It's about the fact that a quantum particle genuinely does not have simultaneously well-defined position and momentum. These properties don't both exist with arbitrary precision at the same time. It's not that we disturb them when we measure. It's that they're not both sharply defined to begin with. This follows mathematically from the wave nature of quantum particles. A wave that is perfectly localized in space, that exists at one precise point, must be built from a superposition of waves with many different frequencies. A wave with a perfectly definite frequency must extend across all of space. You cannot have both perfect localization and perfect frequency definition simultaneously. This is a mathematical fact about waves called the bandwidth theorem. Since quantum particles are described by waves, position, and momentum, which are related to the particle's localization and wave frequency respectively, have exactly the same relationship. You can't have both well-defined at the same time. Not because of measurement limitations, because of the mathematical structure of reality. The implications are staggering. It means that even at absolute zero temperature, where classical physics says everything should be perfectly still, quantum particles still jiggle. They have what's called zero-point energy. If a particle were perfectly still, its position would be fixed and its momentum would be exactly zero. Both would be perfectly defined. Uncertainty principle violated. Nature doesn't allow this. So particles always have irreducible quantum fluctuations. They're never truly at rest. This zero-point energy is real. It contributes to the structure of atoms. It stabilizes matter. Without zero-point energy, electrons would spiral into the nucleus, and atoms would collapse. And vacuum energy, the energy of empty space due to quantum fluctuations, has measurable effects. The Casimir effect, where two uncharged metal plates placed very close together in a vacuum attract each other due to the differential vacuum fluctuations between and outside them, has been measured experimentally. Empty space is not empty. It seethes with quantum uncertainty. The universe, at its most fundamental level, is not a clockwork machine with precisely defined states. It is irreducibly fuzzy, irreducibly probabilistic. Heisenberg didn't discover a limitation of our instruments. He discovered a fundamental feature of reality. Part 11, Quantum Tunneling, the Universe, Cheating Its Own Rules. Here's something that should be impossible. A particle approaches a barrier that it doesn't have enough energy to cross. In classical physics, the outcome is obvious. The particle bounces back. End of story. In quantum mechanics, there's a non-zero probability that the particle appears on the other side of the barrier. Not by going over the barrier, not by going around it, through it, without ever having the energy to be in the middle of it. This is quantum tunneling. And it sounds like pure magic, but it's real. It's been measured. It's being used in technology you carry in your pocket right now. The explanation comes from the wave nature of quantum particles. When a quantum particle approaches a barrier, its wave function doesn't simply stop at the edge. it exponentially decays through the barrier. And on the other side, the wave function has a small but non-zero value. Since the probability of finding the particle at a location is proportional to the square of the wave function, there is a small but non-zero probability of finding the particle on the other side. The thinner the barrier, the higher the probability of tunneling. The lighter the particle, the higher the probability of tunneling. Heavy particles in thick barriers essentially never tunnel. Electrons in thin barriers tunnel quite readily. Now here's where this gets genuinely astonishing. Quantum tunneling is responsible for nuclear fusion in the sun. In the core of the sun, hydrogen nuclei are smashed together under enormous temperature and pressure. For fusion to occur, two hydrogen nuclei need to get close enough that the strong nuclear force, which operates at very short range, can take over and bind them together. The problem is that both nuclei are positively charged and repel each other electrostatically. The electrostatic repulsion creates an energy barrier. The temperature at the center of the sun, while incredibly hot, is actually not quite high enough to give hydrogen nuclei enough thermal energy to classically overcome this barrier. According to classical physics, the sun should not be fusing hydrogen efficiently. The sun should not shine as brightly as it does, but it does shine. Because quantum tunneling allows the hydrogen nuclei to tunnel through the electrostatic barrier rather than going over it. Even though classically they don't have enough energy, quantum mechanically there's a non-zero probability of tunneling, and the sheer number of hydrogen nuclei attempting fusion every second means enormous numbers successfully tunnel. Without quantum tunneling, the sun doesn't shine at its current luminosity. Without the sun, no photosynthesis, no food chain, no life on Earth. You are alive because quantum particles tunnel through energy barriers. Quantum tunneling also enables scanning tunneling microscopes, which bring a sharp metal tip incredibly close to a surface and measure the tunneling current of electrons between tip and surface. By mapping this current, these microscopes can image individual atoms. We can see atomic structure because electrons tunnel. And flash memory storage. The technology in solid-state drives and memory cards and phones works by storing electrons on tiny floating gates, separated from the rest of the circuit by thin insulating barriers. Writing and erasing data involves forcing electrons to tunnel through these barriers. Your photos, your messages, your apps, all stored using quantum tunneling. The same effect that physicists once found bizarre and counterintuitive is now engineered into consumer electronics. The universe is strange, but it is also, eventually, useful. Part 12. Wave function collapse. What happens when you measure? We've mentioned wave function collapse several times. Now let's actually dig into it, because this is where quantum mechanics gets philosophically deep and controversial. A quantum particle is described by a wave function. The wave function encodes all the information about the particle. It tells you the probability of finding the particle in different locations, with different momenta, with different spins. The wave function evolves smoothly and continuously over time, according to Schrödinger's equation, one of the most important equations in physics. While the wave function evolves this way, the particle exists in superposition, multiple states at once, all with associated probabilities. But when you make a measurement, something different happens. You don't get a probability distribution, you get a single definite result. The electron is spin up, the photon is vertically polarized. The particle is in this location. After the measurement, the wave function has changed. It now reflects the definite result that was obtained. The probability of getting spin up is now 100% if you measure again immediately. All the other possibilities have vanished. The wave function has collapsed from a superposition to a definite state. This process, wave function collapse, is described by what's called the Born rule. The probability of collapsing to any particular state is given by the square of the corresponding wave function amplitude. This rule is experimentally verified to extraordinary precision. But here's the problem. Schrödinger's equation describes smooth, continuous, deterministic evolution of the wave function. Wave function collapse is abrupt, discontinuous, and random. These are two completely different kinds of processes, and quantum mechanics doesn't tell you when one takes over from the other. It doesn't describe collapse. It just says collapse happens when you measure. What's a measurement? The theory doesn't say what physical process constitutes a measurement. Unclear. How does smooth, deterministic evolution suddenly become random collapse? Nobody knows. This is called the measurement problem, and it is one of the deepest unsolved problems in the foundations of physics. Part 13. The measurement problem and interpretations of quantum mechanics. The measurement problem has been with us since the 1920s, and different physicists have proposed different solutions, each with different implications for the nature of reality. The Copenhagen interpretation, associated mainly with Niels Bohr, is the oldest and still the most widely taught. It essentially says that the wave function describes our knowledge of a quantum system, not some observer-independent reality. Collapse happens when an observer makes a measurement. The quantum world and the classical world are genuinely different, and the classical world is where measurements happen and results are recorded. Don't ask what the particle was doing before measurement. There is no answer. The problem with Copenhagen is that it never clearly defines what counts as a measurement or what distinguishes classical from quantum. It sweeps the measurement problem under the rug by decree. This bothered many physicists enormously, including Schrödinger himself and Einstein. The many worlds interpretation, proposed by Hugh Everett III in 1957, takes a completely different approach. It says, the wave function never collapses. Schrödinger's equation is always valid, always. When a measurement is made, the measuring device becomes entangled with the particle. The observer becomes entangled with the measuring device. The entire system, including the observer, goes into a superposition of all possible measurement outcomes. But each branch of this superposition is an entire separate world in which one definite outcome occurred. The branching creates parallel worlds, each equally real, each containing observers who experience definite results. The appearance of collapse is because we are in one branch, experiencing one outcome, while all other outcomes are realized in other branches that don't interact with ours. Many worlds has genuine advantages. It's mathematically clean. No collapse, no special role for observers, no classical quantum boundary. Just Schrödinger's equation running forever, generating branches. But the price is ontological extravagance. Many worlds implies an unimaginably vast, constantly proliferating ensemble of parallel worlds, all equally real. Some physicists find this perfectly acceptable. Others find it so extravagant as to be unbelievable. Pilot wave theory, developed by David Bohm in the 1950s, takes yet another approach. It says particles do have definite positions at all times. They're guided by a real wave, called the pilot wave, or quantum potential, that propagates through space and tells the particle where to go. The apparent randomness of quantum mechanics comes from our ignorance of the exact initial conditions, not from fundamental indeterminism. Pilot wave theory is deterministic, and the trade-off is that pilot wave theory requires non-locality. The pilot wave must respond instantaneously to changes anywhere in the universe, including changes at the location of entangled particles. It's explicitly non-local, which Einstein would not have liked. Cubism, quantum Bayesianism, proposed in the 2000s by Christopher Fuchs and colleagues, takes yet another approach. It says the wave function is not a description of physical reality at all. It's an agent's probability assignments, a tool for calculating expected experiences. Collapse isn't a physical process. It's just an agent updating their probabilities based on new information. Reality is what we experience. The wave function is just a calculation tool. Cubism sidesteps the measurement problem by making the agent, the experiencer, fundamental. But critics say it's uncomfortably subjective and doesn't explain why physics is so remarkably effective at describing a shared public world. All of these interpretations use the same mathematical formalism. All make the same experimental predictions. None can be distinguished by any experiment currently conceivable. They are different metaphysical pictures painted with identical mathematical brushes. The question of which interpretation is correct is still genuinely open. And it's not a peripheral debate. It's a debate about what reality fundamentally is. Part 14, Quantum Computing, the most consequential technology being built right now. Let's come back down to Earth for a moment and talk about the most practically revolutionary application of quantum mechanics being actively developed right now. Quantum computing. A classical computer stores information in bits. Each bit is either 0 or 1. Everything your computer does is ultimately just massive numbers of bits being flipped between these two states according to logical rules. This works extraordinarily well. The device you're watching this on is a testament to how far classical computing has taken us. But classical computation has fundamental limits. There are certain classes of problems that are intractable for classical computers, where the time required to solve them grows exponentially with the size of the problem. Even the best classical supercomputer on Earth would take longer than the age of the universe to solve some of these problems at useful scales. Quantum computers use qubits, quantum bits, and a qubit can be in a superposition of 0 and 1 simultaneously. Not secretly one or the other, genuinely both, with probability amplitudes until measured. The power comes from how many states this allows simultaneously. 2 classical bits can be in one of 4 states: 0, 0, 0, 1, 1, 0, 1, 1, but only one at a time. 2 qubits can be in a superposition of all 4 states simultaneously. 3 qubits, superposition of 8 states. 10 qubits, superposition of 1024 states. 50 qubits, superposition of over a quadrillion states. Quantum algorithms exploit this by encoding a problem into a quantum superposition of all possible answers, then using quantum interference to amplify the probability of correct answers and cancel the probability of incorrect answers, then measuring to obtain the correct answer with high probability. This gives quantum computers exponential or polynomial speedups over classical computers for specific types of problems. Shor's algorithm, developed by Peter Shor in 1994, can factor large numbers exponentially faster than any known classical algorithm. Why does this matter? Because the security of most internet encryption, including the SA system that protects banking, commerce, and communications, relies on the classical difficulty of factoring large numbers. A sufficiently powerful quantum computer running Shor's algorithm could break most current encryption. This is why governments and companies are racing to develop post-quantum cryptography, encryption systems that quantum computers can't crack. Grover's algorithm provides a quadratic speedup for searching unsorted databases, not exponential, but meaningful at large scales. Simulating quantum systems is exponentially hard for classical computers because quantum systems have exponentially many states. But quantum computers can simulate other quantum systems naturally using the same quantum mechanical principles. This makes quantum computers extraordinarily promising for drug discovery, materials design, catalyst optimization, and chemistry more broadly. A molecule has quantum mechanical properties that classical computers struggle to simulate accurately. A quantum computer can simulate it directly. We are in the early days of quantum computing. Current quantum computers from companies like IBM, Google, IonQ, Quantinuum, and others have tens to hundreds of qubits, but these are noisy qubits. Quantum coherence is fragile. Maintaining superposition long enough to run algorithms requires extreme isolation, often at temperatures colder than outer space. Errors accumulate. Error correction requires large overheads. In 2019, Google claimed quantum supremacy, performing a specific benchmark calculation in 200 seconds that they estimated would take the best classical supercomputer 10,000 years. IBM contested the 10,000-year figure, suggesting their classical systems could do it in 2.5 days with different algorithms. Even accepting IBM's more conservative estimate, the same calculation, 200 seconds versus 2.5 days, is a dramatic demonstration of quantum advantage for a specific task. Quantum computers won't replace your laptop. Classical computers will always be more efficient for everyday tasks like writing documents, browsing the internet, running applications. Safasuru, quantum computers are specialized tools for problems where their particular computational strengths apply. But for those problems, they represent a qualitative leap in computational power that could be civilization-changing in fields from drug discovery to materials science to cryptography to optimization problems that affect logistics, finance, and artificial intelligence. The quantum computing race is one of the most consequential technological competitions happening right now, and it's entirely built on a century of weird, counterintuitive quantum physics that plenty of physicists originally hoped would turn out to be wrong. Part 15, what quantum mechanics actually means for reality. And now we get to the part I've been building toward this whole time. Not the most practical, not the most mathematically elegant, but the part that I think is genuinely the most important. What does quantum mechanics actually tell us about the nature of reality? Quantum mechanics works. I want to emphasize this. It is the most precisely tested theory in the history of science. Its predictions have been verified to 11 decimal places. The anomalous magnetic moment of the electron, calculated using quantum electrodynamics, the quantum theory of electromagnetism, matches experiment to 11 significant figures. That is the equivalent of measuring the distance from London to New York and getting the answer right to within the width of a human hair. The technology of the modern world is built on quantum mechanics, lasers, transistors, MRI machines, solar cells, LEDs, nuclear reactors, GPS, which requires relativistic corrections, but also quantum mechanical precision in the atomic clocks at its heart. Virtually every piece of technology developed in the second half of the 20th century and beyond has quantum mechanics in its foundations. So quantum mechanics works extraordinarily, spectacularly well. And nobody fully understands what it's saying about reality. Let me give you 3 ways quantum mechanics forces us to revise our deepest assumptions about the physical world. First, the universe is not deterministic. In classical physics, given perfect knowledge of the present state of the universe, you could in principle predict all future states exactly. Every event has a cause that fully determines the effect. Laplace's demon, a hypothetical being with perfect knowledge of all particles and all forces, could calculate the entire future of the universe from any starting point. Quantum mechanics kills this. At the quantum level, events happen with certain probabilities, not certainties. Even given perfect knowledge of a quantum system's current state, the best you can do is assign probabilities to future measurement outcomes. The actual outcome when it occurs is genuinely random. Not random because we don't have enough information. Genuinely, fundamentally, irreducibly random. Bell's theorem rules out hidden deterministic variables. God, it turns out, does play dice. Einstein was wrong about this. Bohr was right. Second, the universe is not locally real. Local realism, Einstein's bedrock assumption, says that objects have definite properties regardless of whether we measure them, machismus, and that nothing influences anything else, faster than light. Bell's theorem and the experiments that tested it prove that at least one of these assumptions must be false. Since faster than light influences violate relativity in deeply problematic ways, the standard conclusion is that particles do not have definite properties before measurement. Reality is not a collection of objects with pre-existing definite characteristics waiting to be observed. Properties come into existence through measurement. Before measurement, they are not defined. This is not a statement about our knowledge. It's a statement about reality. Third, the observer plays a constitutive role, not necessarily consciousness specifically, but measurement and interaction are not passive. They do not simply reveal pre-existing facts about the world. They participate in bringing definite facts into existence. The universe, at its most fundamental level, is not a clockwork machine ticking along with fully defined states at every moment, ready to be read off by an observer who doesn't change anything by looking. The universe requires interaction to manifest definite properties. Wheeler captured this with the phrase "it from bit," the idea that physical reality fundamentally arises from information, from answers to yes or no questions posed by measurements. The universe is, in some deep sense, informational, participatory, constituted by observation. Now, here's the thing I find most philosophically profound about all of this. Despite everything I've just described, the solid, reliable, classical world we experience every day emerges from it. The laws of classical mechanics, the predictability of everyday objects, the stability of matter, the reliable behavior of chairs and mountains and automobiles, all of it emerges from the underlying quantum weirdness through decoherence, through the law of large numbers, through the averaging out of quantum fluctuations when enormous numbers of particles are involved. The quantum world is the real world. The classical world is an approximation, a very good approximation for large, warm objects, but an approximation, which means everything you have ever touched is made of atoms that don't have definite positions until measured. Everything solid is mostly empty space, the electrons surrounding atomic nuclei occupying probability distributions rather than definite locations. The apparent solidity of matter is a consequence of quantum mechanical electron repulsion, not of particles packed tightly together. The color of every object is determined by quantum transitions between electron energy levels. The chemistry of life, the reactions in your cells, the copying of DNA, the folding of proteins, all of it governed by quantum mechanics. Your thoughts are electrochemical signals processed by neurons, whose ion channels open and close according to molecular mechanisms that are quantum mechanical at their foundation. Whether quantum mechanics plays any special role in consciousness is a deeply contested question, but the physical substrate of consciousness is undeniably quantum mechanical. The most familiar aspects of existence, solidity, color, chemistry, biology, are all quantum mechanical phenomena that we experience in their large-scale, classical approximation. And that is, I think, one of the most beautiful and deeply strange things that science has ever discovered. We live in a quantum universe. We are quantum beings. And the solid, reliable world we navigate every day is a kind of emergent classical illusion built on a foundation of irreducible quantum weirdness. So let's bring it all together. Quantum mechanics started from two unexplained experimental results at the turn of the 20th century, the ultraviolet catastrophe and the photoelectric effect. Planck's desperate mathematical fix, discrete quanta of energy, and Einstein's audacious application of it to light itself launched a revolution that shook physics to its foundations. Wave-particle duality showed us that quantum objects are neither waves nor particles, but something fundamentally new that displays wave properties in some experiments and particle properties in others. The double-slit experiment, the central mystery of quantum mechanics, showed us that single particles go through both slits simultaneously as a wave, produce interference patterns, and respond to the availability of information about which path they took in ways that have no classical explanation. Superposition told us that quantum systems exist in multiple states simultaneously before measurement. Schrödinger's cat dramatized the absurdity this creates at macroscopic scales, while decoherence explained why we don't actually see cats in superpositions. The observer effect showed us that measurement isn't passive, that the act of obtaining information about a quantum system changes its behavior. Quantum entanglement showed us that separated particles can be correlated in ways that cannot be explained by pre-existing local properties, that the universe is non-local at its quantum foundation. Bell's theorem provided the mathematical tools to test hidden variable theories, and experiments vindicated quantum mechanics over Einstein's intuitions. Heisenberg's uncertainty principle showed us that position and momentum cannot both be simultaneously well-defined, not because of measurement limitation, but because of the wave nature of quantum particles. Quantum tunneling showed us that particles can pass through barriers they classically cannot cross, enabling fusion in the sun, imaging of individual atoms, and the flash memory in your phone. Wave function collapse, and the measurement problem confronted us with the deepest unsolved puzzle in the foundations of physics. What happens when we measure? Nobody fully agrees. The interpretations of quantum mechanics, Copenhagen, many worlds, pilot wave, cubism, offer wildly different pictures of reality while making identical experimental predictions. Quantum computing promises to harness superposition, entanglement, and interference for computation that is qualitatively more powerful than classical computation for specific problems. And at the deepest level, quantum mechanics tells us that the universe is not deterministic, not locally real, and is constituted in part by the act of observation and measurement. The solid world is built on quantum strangeness, and we are part of it. If your brain hurts right now, that means it's working. Welcome to quantum mechanics.